Like that? Yeah, it seems to work.
We'll probably get started.
Okay.
I guess
I can hold it.
Okay, yeah.
That's probably easier.
All right. For everyone who's attending today, we have Matthieu Dubarry joining us. Matthew and I actually met a number of years ago. Lovely. I highly recommend you if you're in. But yeah, today he's going to give driven battery value. So let's see.
Thank you, Billy. Hello, everyone. Thanks for having me. So I want to talk about my work in Hawaii. And if you want to come to Hawaii, there's an ETS in 3 weeks, so you might want to rush up your travel request. So I want to discuss our work in the past decade or so on data-driven battery diagnosis and prognosis. Not going to talk too much about machine learning. It's purely on the data part. So a bit more about me. I'm from Hawaii, but as you can hear from my accent, I actually was not born there. I was born across the pond in France, and I did all my studies there. So I have a bachelor in technology, specialized in material and physical characterization, and I got 2 master's degrees, one in material science and one in ceramic engineering. And then I did my PhD in Nantes on the French coast on the synthesis and characterization, optimization of materials for lithium battery application. I joined HNEI in 2005, so almost 20 years ago, and I'm now the team leader for the Pacali Battery Laboratory, where we do a lot of work on battery prototyping and diagnosis and prognosis. Our main drive for us in Hawaii is the Hawaii Clean Energy Initiative. That's a law that states by 2045 we need to be 100% energy independent. And right now you might not know that, but most of our energy in Hawaii right now we're importing oil and we're burning oil. So we have tankers after tankers coming every day just for us to have electricity. So it's a big drive for us to, for strategic reason, obviously, somebody stop the boat, we are pretty much screwed. But also it's not really environmentally friendly to bring that much oil into the island. So there's a big push towards clean energy, both for the transportation and also obviously for the normal energy. A bit about my lab. We have a lot of activities. We do a bit of materials and formulation. That's not our main drive, but we have a bit of work on desalination batteries using sodium-ion battery materials to try to remove sodium seawater. A bit of work on electrode optimization, and some interest into waste to electrodes, or can we harvest material to make better electrodes? And a good example, a typical one is, you might not know that, but most of the activated charcoal in Hawaii. So we're interested in that. But our main activity is really the testing and characterization of cells. Doing both field usage analysis, and we have some megawatt system deployed on the grid, and also tailored laboratory testing. And I'll insist on the word tailored a little bit later in that talk. We can do prototyping, and our main drive is to have non-invasive diagnosis, trying to develop cells that we can do that on deployed system, not using the cells and do anything restrictive that will hamper its application. But obviously led to some modeling and digital twins, and I know we can have a debate on the meaning of digital twins, but like a virtual cell, where we can do the prognosis for single cell and for packs. And lately, we did a bit of work on intelligence, but mostly on the data, to generate synthetic data sets to be able to train the. So today, I will go through a little bit of that work with you. That's a picture of my old lab. My new lab is under renovation, but that's kind of the setting we had, where we had around 80 channels for full cells, all the way from 100 amps per channel. And you can see here the same cell we had in the BSS. So we had the same cell that were deployed. And we also have around 45 channels for prototyping, so much lower currents. And a lot of temperature chambers, so we can do a lot of testing. That's a little bit of a roadmap. The roadmap we did, all the steps we think are really important to truly grasp the problem in its entirety. Starting from field usage, trying to understand the specific stress for an application. Battery degradation is going to depend how you use it. So if you want to do really good lab testing, you need to understand how your cell will be used. And that allows to design some testing that's adapted to whatever usage you want on the cell. So typically, the duty cycle should not be constant current if you want to test a cell for EV applications, for grid applications. Then we developed a lot of model-assisted diagnosis and fast, non-destructive diagnosis of batteries. That's the model we developed. Then we can use that model to do prognosis at the single cell level. Then, once we have a good single cell level, we can move to the pack level, which have variations, imbalance, etc. And we believe that's the perfect roadmap to really get a good life estimation of the cell. If we want to go a bit further and to accurate set of charts of health tracking, then we need to develop some algorithm that allow us to automatically. And we need to train those algorithms in big data, and we come up with synthetic data generation to allow truly to have big data with millions and millions of curves to train. So first, the first part, we mainly had two projects. The first one was on grid-tied storage, where we had 3 grid-tied systems. That's a picture of one that was on the big island of Hawaii. And we had at the same time exactly the same cell that we can test in the lab. And we run more than 3. That one has been on the grid for more than 10 years, still doing fantastic. And we have more than 3 years of aging in the lab of exactly the same cells under different conditions. And we also have a project on vehicle storage, mostly on vehicle to grid, to understand the. And we, for that project, we bought some cells that were extremely similar to the cell in the Tesla Model S, and we tested more than one. An example of that. So first on the grid storage, we have 3 BSS systems. One, that one here, was on the northern tip of the Big Island, 1 megawatt, 250 kilowatt hour. It's been on the grid since 2012. And that one is used for frequency regulation and wind smoothing because it's 1 megawatt on a 190 megawatt grid. We had one on Oahu, it's also on 1 megawatt, 250 kilowatt hour. That one was used for voltage variation and power quality. And that's because it's a much bigger grid. Much more people live on Oahu than on the Big Island. And then we had that one on Molokai, a pretty small island. It's a 2 megawatt system on a 5 megawatt grid. So that one is obviously used for reserve and fault response. And so what we really wanted to is understand. And so we analyzed 3 years of usage on second by second usage of an ISS system on the grid. And the goal was to get that spider plot here that tell us the average usage in terms of current, pulse duration. You can see there's a lot of pulses. But you can also see that those pulses, they kind of group into what we call events. Periods where the SOC mostly go down. And so we define those SOC events in terms of SOC swing, how much SOC was dropped during that time, and also the ramp rate, how fast did that SOC change. And the fifth parameter we use is the module temperature. And so from there, we could define what's the average usage, what's the maximum usage, etc. And that's really helped us to define a microcycle like that one. That's 5% state of charge. But that has the average ramp rate, usage, and power distribution. And you can see here that the power distribution of a microcycle is exactly the same as the average power distribution in the full BSS system. So we define a duty cycle that allows us to do a 5% increment. And then we can play with those 5% increment to make a wide array of different duty cycles, from just frequency regulation at high state of charge, plus or minus 5% all the way. We can do that at mid state of charge, or we can do that at low state of charge. And we can do more amplitude to try to look at peak varying. And of course, we can make any duty cycle we want. So we can mix it up and have some peak shaving as well at the same time. And so I'm not going to go into the results. If you want, everything is published, so you can find the results here. Find the paper, please shoot me an email. I'm more than happy to. In terms of vehicle to grid, what we wanted to do is a design of experiment, trying to grid and trying to look at any combined effects. And so we look at the typical price of electricity as a function of a day, and we notice that obviously when the price is high, that's when the. So we define at work and at home, and we design an experiment so we can test that. So we had some real driving for the discharge. Again, we want to make sure that we use it in a realistic way. So we had a database of 100,000 kilometers work. Then we could either do nothing, charge, or do vehicle to grid, then charge. And then drive to work with the real commute back to work, and then do the same thing. And that gave us a big matrix of tests, to which we added some calendar aging experiment that was designed so that we had more points toward high temperature and high state of charge, because obviously, graphite. And again, all those results are published. If you're interested, you can find them. But what we noticed, unsurprisingly, is that the grid was bad because it was additional on the cell. So then we had the idea of what if we modulate the charge? What if we, instead of charging as constant power, which was pulses, always charge, but different amplitude for the charge. That way we can test without actually inducing any additional usage on the. And what we found with our study is actually when we did that, we had zero impact of a frequency regulation on the degradation. So that we could do it without adding any additional usage on the cell, simply by modulating the charge. As you can see here, during the charge, we just, instead of having a constant charge, we just modulate. In average, that's the same current. One with pulses, one not. And for that particular cell, we didn't see any impact, which was really interesting. But under some conditions, the electric grid might be doable for frequency regulation if you modulate the charge. Again, that's published, so if you're interested, please free to get the paper. So just to summarize, we spend a lot of time trying to understand the usage of the cell in terms of what stresses apply to a cell. And from there, I'll show you with a model, we can start to get some really good prognosis of the usage of the cell. But in the interest of time, I'm going to move to the second part, which is really our bread and butter and what we are the most active on, how to diagnose the cell non-invasively. And the importance of that is the path dependence of the degradation. Depending on how you use the cell, and here I take an example of a vehicle, depending on traffic, road type, driving habits, temperatures, charging habits, grid ties, etc. And that has two implications. The first one is on the knee. If you're here, well, what's your state of health? If you're on path A, yeah, your state of health might be 90%. But if you're on path D, your state of health actually should be more around 20% because your cell is about to die. That's what you need to know. That's what a good diagnosis of your cell should be and a good prognosis should be. Because of that path dependence, it's going to be different from every battery out there. Even if we had exactly the same car, built exactly the same day, we all drive differently. So there's no way of knowing which cell is going to degrade faster than the other. The only way of doing it is to diagnose the cell on board. And that's why you need method to be able to give you a good diagnosis on board, because every battery is going to be different. And that raises the question of, okay, what is a diagnosis? That's the question. To me, the diagnosis is a balance between the accuracy you want and the resources you're willing to put. Typically, academia, a balance is tilted like that. We can be extremely accurate. We can use fancy, use years and years of post-mortem experiments, and we can understand exactly how a cell degraded. But that's intrusive, that takes a long time, and that's really expensive. Industry wants the total opposite, right? They want the diagnosis to be really, really fast and cost almost nothing in terms of cost of sensors, energy cost to run the diagnosis. But as a result, the accuracy is typically just capacity resistance monitoring, and it's pretty bad. There's no way you can predict the knee based on that, and it's way too late. So what we try to develop, and when we started that project around 2010, is try to develop the best solution, something that gives us enough, but don't require too many. And so that's why we're starting to think in terms of degradation. Material science. I want to understand what happens. And sadly, when you look inside the battery, it's a mess. Battery not work because the electrolyte is not stable, decompose. The materials shift when they inflate and deflate. And so that summarizes pretty much, I would say, most of the degradation that could happen in your cell. For diagnosis is if you want to, you need to quantify each and every one of them. You need to have a model for every one of them. That's parameterized with the data for your exact same cell. In other words, that's impossible. And so what we proposed, us and others, is to look at kind of a level above that and figure out that, you know what, at the cell level, at the car level, what's really important to know is not why material, it's that I'm losing material. And maybe that's a good enough diagnosis just to quantify how much material is lost. No matter what, it's not now. Call Samsung tomorrow and tell them, stop losing material, please. It's not going to happen. The cell is what it is. It has been vetted by them, and it's not going to change for the next 3 or 4 years. So to us, that was high enough level to understand the cell. So we can classify those degradation in terms of amount of active material, change of lithium inventory, and change of kinetics. Three big families of degradation modes. Because no matter what happened to your cell, you can always decompose that degradation into how much material was lost, how much lithium was lost, how much the kinetic was affected. So if you take the example of the ACI growth, where the ACI growth is going to consume lithium, so you have a loss of lithium inventory. After some while, the resistance is going to increase too. That's the kinetics. And if you clog some pores, you're going to lose material. So you see, I could decompose any of those degradation into some of the degradation mode. So that's half of the battle, right? We simplify the problem from 20 plus mechanisms to 3 families. Now the next step was, okay, how can we access that information? And more importantly, how can we access it with usable sensors, right? A car manufacturer is never going to add 1,000 sensors that cost $10 in their car. That will increase the price of a battery significantly. So we wanted to use what's available: voltage, current, and temperature. Current and temperature, they vary too much with what you're doing. They vary with the environment, so they're not really reliable. Voltage is good because voltage carries thermodynamic information. What that means, if you look at the voltage response of a cell at beginning of life or end of life, you see some small variation on the curve, and those small variation changes. The problem with that representation is if I ask you to explain to me what changed between the black and the red curve, it's impossible, right? We see small variation, but it's impossible to quantify even for us with our brain, with a pattern recognition. So trying to optimize is even impossible, more difficult. So what we decided to do is look at the derivative. When we have a derivative, we enhance those changes. And so that's exactly the same data here and here. And you can see that on the derivative, we have those, so that's a negative curve. So I'm going to call that a peak. But you can see that we have some really well-marked peaks. And you can see that when the cell aged, well, that peak disappeared, that peak increased, that peak disappeared, that peak moved. So that's information. Your cell degraded, and the signature of that degradation were those changes. Now the next step, and when we started the work in 2010, nobody could really make sense of those changes. So a lot of our work was trying to interpret those curves and make sense out of them. And so we end up with is an extremely simple model. I know most of you guys doing physics-based model. My model is much, 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 much simpler than yours. I only use half cell data. So I have positive electrode versus lithium at different rates. Negative electrode versus lithium at different rates. That's it. That's all the parameters in my model. Now the next step is to match the full cell response. So we can play with 2 parameters, mostly, at low rate. The size of one electrode compared to the other. Which electrode is bigger than the other? And we can look at the ratio. That's the information we need, the ratio of capacity, positive versus negative. And we need to look at their offset. And that's pretty much how much lithium was lost during formation. And if you play with that, and if you play with the rate on the electrode a little bit for kinetics, you can match really well the full cell and the difference of the half cell. Again, on the voltage capacity curve, it looks good, but I just show you that that scale means nothing. And that's a lesson for modeling people. When you report the fit of your model, derivate the curve, because you can sell a really bad fit if you just show the voltage capacity curves. But if you derivate, you can see that we match pretty well all the different peaks in terms of position, shape, and intensity. So we replicate exactly the electrochemical response of the cell. We build a virtual cell that's identical to the real one. And we can do that fit at beginning of life, and we can do the fit at end of life. And how the parameter changed, that's how the cell degraded. And we can relate that to the change of active material, change of lithium, change of kinetics. because we can decompose each and every one of them individually. And that model is really fast. We can do hundreds of thousands of simulations a second without a problem. But that's a really simple view. It's at low rate, not really kinetic, there's no really complication. So we can look at plating. Plating, if you think about it, that's a blend. Your negative electrode, you have graphite, and when you run out of graphite, you can plate the lithium. So it's a blended electrode, graphite and plating. So you can simply add another phase in the model, add the plating potential of your metal, whether it's lithium or sodium, if you want to use sodium. And so when the model detects that you don't have enough graphite left, whether because you lost too much or the resistance increased too much, it automatically can add plating. Also, we can change the kinetics. Oh, so finish on that. We can predict it, and we can play on the reversibility of that plating. If plating is irreversible, you're losing lithium. So that's a loss of lithium inventory. Plating by itself does not induce any capacity loss. We're doing half cell all the time. We can plate and strip lithium easily. Plating by itself is not a degradation. Degradation is easy. Lithium inventory. Plating is not a degradation mode. The degradation mode is the loss of lithium inventory, because that lithium is lost. We don't know where. Mostly it's dead somewhere on the electrode, and it could be reconnected under some cases. But we can play on that, the model, right? We can select any amount of loss of lithium we want. So we can, as a parameter, set the reversibility of plating. And that allows to simulate paths like that one with reversible plating, and paths like this one where the plating is not reversible, and we can predict that acceleration. So that knee, we can predict it from the start, because we can predict the rate of loss of negative, we can predict the rate of loss of lithium, and we can set the reversibility. So the knee, predict it. That's one of the possibilities for knees, but with that model, we can predict it. Now, that curve is really interesting, and I really enjoy that one. That's to showcase the impact of kinetics. If you think about it, kinetics is just slowing your cell. If you're decreasing the kinetics or improving it, if you have faster kinetics. That's the same effect, increase the current or decrease the temperature. So what that means is if we test different rates, and if we play with that, we can derate the electrode level so that we can match fast lower temperature by increasing the rate. And in that example here, I use data at 25 degrees in black to simulate data at 10 degrees by increasing the rate on my electrode, or data at 40 degrees by decreasing my electrode. And you can see we can get really, really good fit. And even further, oh, I should have one more slide here, but oops, way too far now. And we prove that actually the variation of the parameters fit an Arrhenius law. So if we have 3 points, we can calculate the Arrhenius slope, and then we can simulate any temperatures from the room temperature data. A really simple step of calibration. We can also do blends, and I show you that for plating, but we can do any of the blends. And what we added recently, to realize that in most cases, in most models, when you do blending, you assume current on both components of the blends. But experiment with a really good, I don't have a reference here, a really good group in Germany that did some fantastic experiments to showcase that actually current density is not the case at all. It's not constant current in some cases. Yes, if you have LFP-LMO, when the voltage response are completely separated, yes, it's constant current. But actually, both phases see more current because they see all the current at a time. So if you have a 50-50, LFP and LMO are seeing twice the rate because all the current density is coming to one phase at a single time. But you can see that for overlapping response or partially overlapping response, then the voltage variation, the current density is much more complex. And that's affect a little bit the voltage response of the cell. So in our model, we can adjust that, but we just proved recently, and we published a paper in batteries where we showcase that at low rate, we have a big impact. But for faster rate, it might have an impact. So if you want to diagnose the cell on a blend, you might want to take that into consideration. For material nerds like me, I really like that one. You probably heard of voltage fade. Voltage fade means that sometimes when the cell cycle, you change the structure. Right now, everything I showed you assume that your material don't change with life. But sadly, some materials do change with life. But we can also handle that with a blending. We just start with one phase is 100%, and with cycle, we have more and more of the other phase. That way we can simulate a transition from one phase to the other. But for the material nurse, does that happen as a solid solution or does that happen as a phase transformation? It's not the same thing. If that happens as a phase transformation, we have gradually one phase turning to the other. And so if we take a completely hypothetical alchemic material turning from LFP to LMO, it's just for the example, it's not possible in real life. But you can see that we start from the LFP plateau, and then when we increase the amount of LMO, we start to see more and more of the LMO plateau until we have only LMO. And in a way, if you think in terms of derivative, one peak disappears and one peak is growing. But if you have a solid solution, you're going to gradually go from one to the other. In a way, the black peak is moving towards the blue peak. Same initial point, same final point, completely different path in the middle. So we can do both. Oh, it's stuck. Oh, wait, it's back. Oh, perfect. Okay, so from now we focused on really homogeneous small single cell, where we all know that the larger we go, the more at risk of inhomogeneities we have in the cell. The good thing is that model is so light in calculation that we can easily put as many as we want in parallel. So we can simulate a segment itself. We can have a lot of little segments in parallel with all different parameters and see what impact it has on the full cell. In a way, in that case, that's a pack model if you separate all the electrodes like that. But that could work to some degree for a single cell. But for a single cell, you also want to consider, and I don't have the slide here, but we just published a paper where we also consider the paralleling at the electrode level. And look at the difference at the full cell when you do the paralleling at the using small full cells or do paralleling at the electrode and then calculate the full cell. It's not the same thing. And which one happened in real life? Where when you rest, the paralleling is only at the electrode level. But when you use the cell, both of them are probably happening at the same time. And that influences the voltage response of the cell. So that's something you can only do with a model that's really fast because you need to parallel a lot of them and run a lot of calculation to be able to try to see the effect. So we just published on that. And if you're interested, I can send you the reference of the paper. Lastly, all I showed you right now is constant current simulations. And we all know that that's not really realistic. If we want to have something that's applied, we need to be outside of constant current. And so the way we can circumvent that is that where if I can do simulation T versus rate curve. So I have a table instead of just a single curve. Do that, you can select for every state of charge, you can select the power you want, or the voltage you want, or the current you want. And that allows to simulate constant current and constant voltage. That allows to simulate constant power, and that allows to simulate any duty cycle you want. And to illustrate that, we worked on irradiance, and I'll show you an example of that when we talk about big data. But to summarize, that modeling approach, and whatever you want to call it, the mechanistic modeling approach, the degradation mode approach, I don't like the OCV modeling name because you can do it outside of OCV. You should not do it on OCV because with hysteresis and all this kind of stuff, it's not working well. Your curves need to be polarized, so you should not do it on OCV no matter what. So call it whatever you want, degradation mode approach, mechanistic, whatever. But that method has been proven extremely useful, and it's grown significantly since we pioneered it in 2012. We can do any degradation mode, we can do material prognosis, we can look at constant current, blends, overcharge, over discharge. We can do big data, I'm going to show you that. We just proved recently that we can do it on sodium ion, on blends, in homogeneity. So that's the stuff we're working on, but we recently published a string of paper on that. And if you want to play with it, you can get a graphical user interface to play with. Even go to the HNEI website. We embed it in the HNEI website now. So you can play with it on the website in a really crude version of the model, but you can. And if you want more access, we can discuss, collaborate, and I can give you more access so you can do overfitting and looping to do calculation more faster. Right now on the toolbox, you can only do them one by one, which is useful, but not great to analyze a ton of data. And if you're industrial, we can talk licensing. And we have licenses all over the world. We have a lot of great universities. Actually, you have a license, Billy, or someone here has a license? Or point? We have a lot of universities. We have nearly all the national lab in the US, industrial as well. But at some point, license them. So to do prognosis, well, what we recommend is to do several diagnoses, at least 3, and then try to extrapolate on the degradation model level so that you can predict the needs. And we showed many times that you can predict some needs that way. So it's a much better diagnosis than just looking at capacity and power. And that's an example. So that's 2 cells, exactly the same cell, exactly the same match. The blue one was doing 4CD. The black one was 3 hours of driving and 4C. So on paper, far less aggressive usage. And you can see that after 600 cycles, they pretty much lost the same pace, right? It's linear, that's what we expect. If you look at the spec sheet, those cells were. But we could predict that the black one, and we knew that, and we were right. And we knew that, oh, sorry, the animation is screwed up. We knew that because when we looked at, not used to that clicker. When we look at the derivative, we could see that the change were not the same. And we could see that for the black one, we were losing negative electrode 8 times faster than the blue one. And we were irreversible. And so when we extended those trends, that or we predicted that the capacity was going to dive. Right. And we could have done it as early as cycle 250. We all that bad cell was in trouble. Oh, prognosis, diagnostic. Okay, I'll skip on the summary. We just spent a lot of time on that. Moving on to the last part, pack modeling and the. So we really wanted to have a battery model that was extremely flexible. We wanted just to have to scale up. We wanted a model where for every single cell, we could simulate, every possible degradation. So we naturally embedded our model into a pack model. Then we added a layer to simulate cell-to-cell variations. I have a distribution of capacity, a distribution of rate. Then we developed a paralleling model to be able to parallel the cell properly, taking into account their performance and their voltage response at different rates. And we also developed a model to track the imbalance. It's a really simple model on measuring 2 rest cell voltage. So if you know the rest of the cell, of all the cells in the pack, at 2 points fairly close, you can quantify the imbalance. Don't have really much time. I love that model. I don't really have much time, but interested, we have a paper on it. And then try to control that battery pack. The battery pack be realistic. So be able to control the pack. And we think that with that, we have a battery pack model that is extremely flexible. We can simulate possible degradation in any cell. We can change the level of cell separation, track any imbalance if we need to, and we can control it in different ways. And that's an example of some work we did with Warwick years ago on the impact of homogeneities on the first cycle. And we look at the impact of imbalance in SOC homogeneities, instead of RF homogeneities, capacity homogeneities, and all of them at the same. And we did that for different pack configuration, from all in series to all in parallel, mix of both. And we have some really interesting results on the performance of the pack depending on the type of inhomogeneities and where to look on the voltage curve to assure those inhomogeneities. Actually, I have a slide on our imbalance method. So the way we did it is a really simple graphical method. So follow me. If we have 3 cells in a string, and if initially they all had the same rest cell voltage, we know that the voltage of a pack is going to be the sum of those 3 voltages, right? If they're in series. Now, if you discharge a capacity Q, then you're going to reach a point rest 2 on all 3 cells. And again, the sum of the voltage of the 3 cells is going to be the voltage of a pack. But you cannot really say for anything for this, any point in between. But if you scale and translate the packs, the cells, sorry, so that you match vertically the first 3 points and vertically the last 3 points, then it's true for every point. So it's a really simple approach. We just scale cells. But once we do that with 2 parameters, the translation factor and the scaling factor, now we can sum every point and get the pack response for any. You can fit it to find side. By playing with those 2 parameters, we can simulate possible. And obviously, those OCV curves, we can change on the degradation, the cell-to-cell variations, and all of that. It's an extremely simple model. Extremely efficient at replicating the impact of imbalance. And that's an example of the impact of balancing depending at where you lose capacity. Do you lose capacity in discharge? Do you lose capacity? Do you lose capacity doing both? Then the best balancing might because your capacity, the spread of cells at different stage of the cell, end of charge or end of discharge or both. You can play with that. A lot of that still need validation. That's just a concept. We just need a lot of data to try to validate all of that. We can simulate any possible type of imbalance, different type of balancing. Okay, let's talk a little bit about the big data aspect. I'm sure you will notice that in the past decade now, there's been an exponentially increasing amount of paper using machine learning to take a peek, diagnose the cell SOC, state of health, remaining useful life, whatever. But most of those papers is they use a couple of cells to algorithm. And typically constant current, slow rates. And so it's not enough data, and there's little to no effort on the data part to train your algorithm properly. And that's a problem because of the path dependence. You want to make sure you train your algorithm on the data. So if you deploy it, it's going to be efficient. Even the best work, well, one of the best work on the topic, the Stanford paper, one of the first one, you have 124 batteries. Yes, that's a lot. But when you look into it, they only change the charge and not by much. The discharge is constant current and all the same. So it's not really a varied data set. It's not representative usage of that cell ever, whether it's on the road, on the grid, on the satellite, whatever. It's not representative of any of that. So we believed at the time when we started working in math in 2017 that there was a need for more data. And maybe creating synthetic data was the solution. Add more data to the experimental one. And I just told you that our model, we can simulate any possible degradation. So I can just take that sentence by the letter and simulate any possible combination of the parameters. And the benefit of that is an experiment. And an example here, it's a testing we did for a year, and that's the 0.25 change. Once we diagnose it, and in that case, it was linear, and we had a bit of loss of lithium and a little bit of loss of active material, we have data that's pretty much indistinguishable. That took a year. That took less than 2 milliseconds. But that combination here is just one point in the 10-line diagram of all the possible combinations. But nothing prevents us to simulate all the other combinations, right? It's not supposed to be a red triangle. It's just every point here is 5,000 points. It's the combination we tested. And we can do that at different cycle numbers. And that gives us those kind of 3D lookup table. And every degradation path, every usage is a path within that triangle. Maybe it starts from here, and maybe it's linear. Maybe it goes like that. Maybe it goes like that. It doesn't matter. We have every possible combination. We can just which degradation we want. And that allows us to simulate synthetic data sets, and we publish them. They are available freely in the literature. We first started with the LFP, NCA, NMC A11 versus graphite data set. More than 5,000 combination with 0.05% resolution, that's 700,000 curves per chemistry available in the literature. And then we simulated different duty cycles, meaning different evolution of the loss of each other. And so we simulated more than 125,000 of them. So as a result, we published more than 3 million voltage curves that you can today download and play with. And with different amount of plating, loss of lithium, exponential increase, whatever, it's just varied. And feel free to design your own. Choose your own equation for the degradation and simulate your own variation. All you have to do is go and fetch, wrong side again, go and fetch the right curve inside that lookup table. And so once we have that, now we can start to see if method works or not for diagnosis, and if they work on every possible combination. So here's an example of our diagnosis method when we track different features on the curve. And we did it for the 100,000 duty cycle at cycle 10, 100, 400, and 1,000. And that's the error in the estimation of loss of lithium, loss of positive, loss of negative, and capacity loss. And you can see that for our method, the error is extremely small for all 100,000 different duty cycles. And we can push the analysis further. Now we can go back to a triangle and see where the method works the best. You see here we have a little spread. Why do we have a spread? Well, because the method is not working great when we have a lot of loss of negative. It's working worst when we have a lot of loss of negative. Now, we can do the same thing for prognosis. And remember what I said about the Stanford paper. Again, great paper. I'm not saying it's a bad paper. It's a really good paper. But they said in their paper that the variance at cycle 100 is an extremely good indicator of state of health. And I think they give a correlation coefficient of around 0.9. Well, when you do it on a varied data set, the correlation is not that good. The correlation is around, actually worse than just looking at capacity loss. But they didn't lie. Don't get me wrong. If you look at the triangle, when you test cells with a lot of loss of lithium, yes, the correlation is 0.9. They didn't lie. They just didn't test their algorithm on a wide enough data set. And so if your application only has loss of lithium, yes, the algorithm works perfectly. But if you take the risk of having some loss of a lot of positive electron loss, the method doesn't work at all. And that's important for application. If you have a car, whether the car is in Hawaii, in London, in Alaska, in the Alps, it's not going to degrade the same. Test all of that. Are you sure that all the possible degradation for your customer is within that range where the method works? If you're not sure of that, then that's probably not the right algorithm for you. So that's to show you one of the benefits of a synthetic data set. Yes, 90% of those might be impossible to get in real life. I absolutely agree. But that's not the point. The point is, here you can test whether or not your method will work on everything or not. And if it doesn't, that gives you some work in terms of design to make sure that those conditions cannot happen in real life. And for us, that's the diagnosis method we have by forecasting the degradation mode. And we can get much better correlation coefficient using that method, using the same data set. So let me show you a last example. And after that, I promise I have time for questions. Can we push that even further? That was constant current. Can we do it outside of constant current? So we decided to try with irradiance. So assuming a battery is connected to a PV system to charge every day. And if you know where your PV system is, the time of day, the day of the year, and the orientation and tilt, you can predict how much. So we did it for 2 years worth of data. We calculated the clear sky irradiance, and we generated the synthetic data set on it, every possible degradation. And we use that to train several machine learning algorithms. And here I take the example of a one-dimensional neural network. And then to validate, we wanted to see how cloudy the day can be for us to still be able to diagnose. So we did the same thing, the same calculation, this time on the real irradiance. And that's our result. So I just want to point out the amount of data that's on that plot. It's 720 days 10,000 degradation per day. And for each of those degradation, up to 25% in 1% increment. I think it's around 80 million points that's summarized on that plot, just to show you big data. And what we found is the average of the accuracy of a diagnosis, well, when there's no clear sky, it varies a lot. Some days you diagnose really, really well, some days it sucks. And it gets to if you have just constant low cloud, then you don't have, it's not sunny, but it's pretty constant for the method work. But if it's a lot of passing clouds, it doesn't work at all. But you can see that above 50% clear sky, the error kind of plateaued, and we have almost no more outliers. So that showed that for 50% or more clear sky, which for us in our is 1 day out of 5, we can the cell perfectly. And that's enough. Remember that your cell is supposed to last a decade. Now calculate in your head 20% degradation in a decade, how much degradation is per day? Is 0.00 something. So you don't need to do it every day. And certainly don't do it every second. Like you see some paper with cloud, I want to diagnose every second. The claim of a degradation model has to be 0.00000 something percent, which is completely unrealistic and unnecessary. Anyway, going back to the topic, we see that 50% of more clear sky, it works great. And then we can go back to the triangle. And you can see here, it's a boring blue triangle. But that's what we wanted to see. That means the error of our approach is independent of the type of degradation. It works equally for all possible degradation. You can deploy that algorithm without worrying. We prove that whatever the cell degrades, the method works. And we can do it. It works the same way from 1% degradation over up to 25% degradation. Again, synthetic data. You can try every possible combination, and you can gather statistics that would be impossible to get from real data. So we're still working on it. We're still trying to complicate things. We're still trying to make it even more and more realistic. And so you should expect more work from us on that topic in the future. Just a few words really quickly on our work on materials. We did a study on electrode optimization when we wanted to look at the impact of different additives on the performance of some LFP and LTO cell in collaboration with Montreal. So I love design of experiments. I love them. I think we should go into battery studies to truly use statistic method to design and do only the experiment need and extract. And in that case, it was a 4-dimensional mixing design. And so we end up having those, I love that figure with those tetrahedras with the impact of all the parameters and how it works. And we worked a little bit on desalination batteries where we try to use sodium-ion battery materials to intercalate the sodium and so get from salt water to fresh water. Well, that's exploratory, still a lot of work to be done on that. And with that, was a bit long, sorry, but just to show you that we are active on a lot of different aspects and we work with a lot of universities all around the world. And I'll be more than happy to cooperate with any of you. With that, obviously, thanks for all of my funding, mostly ONR, they've been great partners, but also a lot of industry working with us. Thank you. I'll be happy questions you may have. Thank you. I think publishing more and more synthetic data and proving that they're exactly the same as the real one. And I think I know you guys did a little bit of that, and collectively we need to do that. And when you review a paper on machine learning, if they use a voltage-based method, and if they use one of the data, say, hey, you guys should do it on the synthetic data, whether pointing to yours or mine or both. And typically I point to both, to all data set I know of. That's how you're going to change people. To explain to them that, hey, if you just validate on that data set, it's not varied enough to make the conclusion. You cannot, and even big team, when you do it, if you look at one of your Jeff Dan's paper on the million miles batteries, that's BS. They did constant current. They have no proof that cell would do million miles in a vehicle because they tested constant current. So it is still a problem of culture. It's changing slowly. I mean, the thing you guys accept as normal is not the thing we accepted as normal when we were younger. I mean, when I was starting, when I was your age, people believed the knee was, oh, something happened right there and the cell went into a knee. People believe when it was your age that hey, when the resistance increased, the capacity decreased. Now you guys don't believe that anymore. So it's going to take some time. It's going to take some education. It's going to take all of us to pinpoint that hey, you guys should use, if you only voltage based, you guys should use a synthetic data set because it's varied and it's. I mean, you can pinpoint on paper when we explain that the Stanford data set, they're right, but they're not varied enough so that you can make a global conclusion. So it's, yeah, it's me talking, it's Billy talking, it's all of us collectively remembering that, hey, synthetic data set for that particular niche is better than real one, or she complements real one really, really well. Kinetics for sure, inhomogeneities and kinetics. You can pretty easily know which electrode is limiting, so that tell you where the capacity is lost, and spoiler alert, for graphite-based cell, it's loss of lithium, period. It's any paper that claims the capacity is lost because of something else is most likely wrong, unless towards end of life when the loss of positive can impact, but it's extremely rare. The loss of negative cell because you have a plating that protects capacity loss because of the negative. So that one is easy to get. On even LTO cell, it's easy to get. The loss of positive is really easy to get on because at high voltage is really easy to get. Be a pain, especially when kinetic degrades, when you lose all the features that indicate you have a loss of negative. That one could be harder. Yeah. Yeah. Okay, so peak area is peak intensity is tricky, especially for cell like LFP when the peak is really, really thin. And the intensity of the peak, I don't really fit it because it's really sensitive. How much smoothing you need, all of that's gonna affect the intensity a lot. I think the area is a much better indicator. The position, it's not. I mean, it depends on the peak. What I would suggest, and that's what we did in 2017, is try all of them. I mean, you can synthesize the data, use the synthetic data we have, and select whatever feature you're interested in and see how much it varies with different degradation. And we have a 2017 paper when we did that. We tried a lot of different features of interest to see how much they vary with degradation. And you're going to see that some, it's perfect, and then it's not working anymore. So do your homework. Synthesize your own data, take hours, and try whatever feature you think is interesting, the intensity, the area, whatever, and see if it works or not. Intensity, I don't recommend it. If you can, take the area. It's much more precise and it's much less sensitive to smoothing. And if you do smoothing, do it at the voltage scale. Do not smooth IC curve or DV curve. Smooth the voltage, then derivate. It makes a big difference. And we have a paper on that we published a few years ago. Yeah, we did. Yeah, so we did. So basically for diagnosis, the way we did it in the 2017 paper is we prove that looking at one variation at the same time, it's never going to give you a crystal clear answer for a machine. Human eye consider a thing. For a machine, one feature of interest is not enough. But we show that with three at the same time, if you choose them carefully, you can, by putting all of them in a 3D space. And then the meshing you do on that 3D space is going to depend on the accuracy of your sensors. So if your voltage is 5 millivolts, 10 millivolts, you take that into account, and that will give you automatically the error on the estimation. I think with the synthetic data, you can pre-calculate everything, and that could be enough. I mean, define what you want. It's just a mechanistic model. Still think the amount of combination you need to consider. I mean, you need to consider the loss of lithium, the positive, the negative, kinetic of a positive, kinetic of a negative, no blame. If you want a 1% accuracy on them, that's 100 to a factor of 12 parameter you need to scan. I don't think that's realistic on board. Making the synthetic data first, having a 3D lookup table might be a better option because you can probably get it, depending on your resolution, within a gigabyte, which should be manageable. Otherwise, cloud. But cloud, do it once a week, once every 2 weeks. Is again, no point doing cloud diagnosis every millisecond. It just doesn't make sense at all if you really think the accuracy you're claiming. Yeah. So that's a really good. We paper like 2 weeks ago on that, and it's just right now it's just trying them all individually without any combined effects. And the next step is to do that through a lot of cycles to see how they evolve and how they can feed on each other. For example, the resistance might, on some case like graphite, if you end up at end of charge on the graphite plateau, and if your inhomogeneity is there, it's not going to balance itself because you're on a plateau, there's no driving force. So when you restart the next cycle, then you have the SOC inhomogeneity that you might not have the cycle before. So we're still looking into all that add up with time. But I think the initial framework, we just published it. It needs a lot of validation because nobody's done that before. And we just published, but we talk about that different paralleling and the impact of it. And there is some impact. Long range, it will play a role because even for small homogeneity, we see change of rate on all the segment. And so if degradation depend on rate, then down the line, those little small variation might have a really big impact. But that's frontier. It's going to require a ton of validation to make something that's solid enough so that we can use it. So far, I think we just laid the background for it, but it's going to take a long, long time to get something that's solid. But it's a big issue.
The last question, to broadly stay on time. So, ignoring silicon, graphite is probably the most dominant anode material.
Yep.
But even within graphite, you've got natural graphite and synthetic graphite, and they often blend them together. Do you see much variation in natural versus synthetic, or can we just take a graphite OCD clip and say that's it, we're done?
But we never look at that in super details, but we notice that depending on the manufacturer, sometimes the graphite are quite different. And we see it on the length of all the plateaus, and we see a lot of variations there. Even some, I mean, the A123 back in the day had a really strange graphite with some double peak at some point that was not quite make sense. And it's probably because of that. But that's something we need to be really careful about because the method people always use to calculate the loss of graphite, they don't understand it. And the way people do it usually is taking the stage 2 peak and all the way up to the end where the graphite should be limiting, which they never verify, but luckily for them, it's most often is. And then that should be 50% of the graphite capacity in theory on a pure theoretical graphite. But if your graphite is blend or something, or if you have silicon, that might not be the case. So again, if you use a method, try to understand the theory behind it rather than blindly saying, hey, those two peaks, that's the graphite negative, that's the loss of graphite. Well, that might not be true. And if you understand exactly how it works, it might not be the case. So to answer the question, yes, there is a big impact, and you should try to always use the graphite for the same cell that you're trying to simulate.
So let's give you another round of applause. Email this.
Yeah, if you have any question, if you cannot find any of the papers, let me know. But most of them are open access, so you should be able to get them.
Super interesting. Yeah. No, I think that was perfect. We've got different coloured bins outside.